All right, let's dive into one of the most basic, fundamental things a computer does, probably hundreds, if not thousands of times a day for you. And that's just finding things. I mean, really think about it. You're searching for a contact on your phone, a specific file on your laptop, a word on a web page, and the answer just pops up, like, instantly. But how? How does a computer actually sift through potentially billions of items to find that one thing you're looking for in less than a second? Well, it turns out, this is one of the most classic problems in all of computer science. You could almost call it the search for everything. And it doesn't matter what you're looking through. You could be flipping through an old-school paper dictionary to find a word, or your computer could be scanning a giant database for a specific profile. The core problem? It's exactly the same. You've got this massive collection of stuff, and you need to find one single, specific match. So let's say you had to solve this problem from scratch. How would you do it? You'd probably go for the most obvious, most intuitive method first, right? Which, as it happens, is also the slow and simple way. This approach is called a linear search. And honestly, it's exactly what it sounds like. You just start at the beginning of the list and you check every single item one by one in a straight line until, hopefully, you find what you're looking for.
Okay, let's make this real. Imagine we're trying to find the letter A in this jumble of items. With a linear search, you start right at the top. First item is the number 8. Is that A? Nope.
So we move on to the next one. K. Still not it. Then the 9. Nope. Then the 2. Nothing. And then finally, on the 5th try, boom! There it is. We found our A. It's simple, for sure, but you can probably already see the problem. This could take a long time. And this is where we get to the heart of the issue. You have a best case and you have a worst case. The best case? You get super lucky. The thing you're looking for is the very first item. One look and you're done. Awesome. But the worst case, the worst case is bad. The item is at the very, very end. Or even worse, it's not in the list at all. In that worst case scenario, you have to make n comparisons, where n is just the total number of items in your list. So if you have 1 million songs in your music library, you might have to make 1 million checks. And that's the fatal flaw right there. It just doesn't scale.
So, there's got to be a better way, right? Of course there is. Let's talk about a much smarter way to search.
You know, the secret actually comes from something we all know how to do, using a dictionary. If you're looking for the word zebra, you don't start at page 1 with the A's, right? No, you flip it open somewhere near the end. This quote here absolutely nails the big idea. With every single guess, you can eliminate half of all the possibilities. This incredibly clever strategy is called a binary search. It's what's known as a divide and conquer algorithm. The name says it all. Instead of going one by one, you just keep chopping the problem in half over and over again. Okay, so how does it actually work? It's basically 4 simple steps. 1, you look at the item smack dab in the middle of the list. 2, if that's not it, you just ask yourself, is the thing I'm looking for higher or lower than this? 3, you take the entire half of the list where your item can't be and just get rid of it. And 4, you just do the whole thing again with the half that's left. All right, let's see it in action. Let's say we need to find the number 57 in this list. Step 1 of our binary search, go straight to the middle. So the middle item here is 71. Is that our number? Nope, but here's the magic. We know 57 is less than 71. And that means we know with 100% certainty that 57 cannot possibly be anywhere in the right half of this list. So we can just ignore all of those numbers. Gone. And that's the real power here. In just one single step, our search problem literally got twice as easy. And we just keep doing that. Chop, compare, chop again, and we can zero in on the answer unbelievably fast. Okay, so this sounds amazing, almost like magic, but there is one very, very important catch. A tiny little rule that makes this whole divide and conquer thing work at all. And here it is. Binary search only works if the list is already sorted, right? Think about it. You can't jump to the middle of a totally random, jumbled up list and learn anything useful. You need that order, that structure, to know which half you can safely throw away. So that brings up the next obvious question, doesn't it? If this super fast binary search needs our data to be sorted, well, how do we get it sorted in the first place? You know, a really good way to think about this is sorting a hand of playing cards. Imagine you're being dealt cards one by one. What do? You take the new card and you slide it into its proper place among the cards you're already holding, right? You keep a sorted section in your hand.
Well, that exact method has a name. It's called an insertion sort. It works by building up a sorted part of the list, just one item at a time. It grabs an unsorted item, finds the right spot for it in the already sorted part, and just inserts it. And that sorted section just grows and grows until, eventually, the whole list is in perfect order.
So, what we have here are two totally different ways of finding things, and each one has its pros and cons. It all comes down to this fundamental quest for speed and efficiency that drives so much of computing.
So let's break down the trade-offs. Linear search? Super simple, no prep needed, but its speed is directly tied to the size of the list. The bigger the list, the slower the search. Binary search, on the other hand, is ridiculously fast. Its worst case is what we call logarithmic, which is really just a fancy way of saying that even if you have a billion items, it'll only take about 30 steps to find anything. I mean, that's insane. But you've always got to remember the catch. The data has to be sorted first.
So what's the big takeaway here? It's that there's almost always a trade-off between doing work up front and getting speed later. Sometimes it's absolutely worth the effort to sort everything first, just so you can have those lightning-fast searches whenever you need them. And it really makes you wonder, right? If something that seems as simple as a search has all this elegant hidden complexity underneath, what other kinds of digital magic are we completely overlooking every single day?